Alrighty, so guys, don't forget your lab number 1 is actually due this week. So if you still have been dreaming, now it's time to wake up, right? You really got to complete lab number 1. Otherwise, you will suffer quite a bit from for the subsequent labs. It's not too late to wake up now, okay? So lab number 1 will be due on, I believe, midnight on Thursday, right? This coming Thursday. The TA will start attending the labs from this week. You can definitely talk to the TA. I will try to be there as well, or at least in my office during the hour. So you can also drop by my office if you want to ask me any course-related stuff. It's more like an additional office hour. Well, we can make it more regular later. Right, the TA contact information about Andy, you can reach out to him on eClass, right, if you need it, and also office hour. Right, nothing else to say. I'll remind you again on Wednesday about your lab number 1, okay, deadline, okay, just make sure you submit in time, no extension, please submit in time to claim your credits. Any questions? All right, let's now do a quick recap and then we'll continue with our math review. All right, so last time we actually finished some very important running example about how to compare 3342 and 4315. So these are the kind of unique formal methods course in your software engineering degree. So it's really worth spending the time comparing the two approaches. You will definitely see that if you talk about, there's no silver bullet to really say which one you should really apply, for every scenario. I would say anytime you got something that wouldn't be so possible for you to restrict the domain of your types, like you have to argue with the integer or maybe some very big interval, then you may have to go for theorem proving. In other circumstances, if your algorithm really depends on some very discrete and small types, in that way, you may want to go for model checking, as you will see in the subsequent labs that we'll see. All right, so we kind of started with the counter example, and then we talk about some, just the process of doing theorem proving. You have to somehow formulate the proof obligation, with respect to the pre and post states, and then we talk about this particular example. And then we just get some feel about what you did in 3342. So that's kind of the process you have to go through in order to do theorem proving, okay? So it is really important to really know the two remarks over here. So once you have already discharged one particular proof obligation, you basically cover all the possible inputs satisfying the type. You don't have to restrict how large the input should be. And also there's no concern about state explosion, which we do for model checking in this course. All right, so that's about theorem proving. And then we move on to the model checking approach, or algorithmic approach. The essence of that, about the algorithm that's being applied, is the depth first search, about building graph, maybe on the fly, or maybe 2 passes. It really depends on how the model checking tool is being implemented. That's the detail you can find out, but it's not required. You can just use the tool. All right, so we talk about reachability graph. You really want to make sure you understand what it really means. So for any checks you want to do in TLA Plus, every time, maybe after you have translated your Pascal into the label transition system in TLA, you will have to somehow prompt the tool to build a reachability graph whenever you want to check some invariant condition. So we talk about kind of build on, from scratch about building this reachability graph. Just get some idea, right? That's basically what's going to be done automatically on TLA Plus. So once we build a reachability graph, let's say in this case we got 1, 2, and 3. 3 states in total, which is finite and small. Pretty good. So it definitely fits into the model checking approach that can terminate. So in that way, we can basically, the tool is going to check for this state, and this state here. It's more like a universal quantification, right? To say for every state in your reachability graph, the invariant property must hold. That's really what we're doing. So think about model checking in some way is like checking some universal quantification. And the universe of disclosure is about all the states in the universe of all the states in the reachability graph. We'll talk about universe of disclosure when we review predicates. Okay, just remember. All right, and then we talk about this general flow about using a model checking engine. So of course, here we talk about TLA Plus, which is what we're using in this course. But in general, there are other model checking tools out there. So just in case, if you decide to use a model checking tool for your maybe engineering work, you can also Google to see what's out there. Okay, so there are many model checking tools out there, and there are even some very nice, like an academic survey paper to really compare the performances or expressiveness of different model checking tools. Right? So there are many resources out there for you to use. All right, so given the module for Pascal and given some properties you want to check, deadlock freedom or maybe invariant property, and we're going to get 3 possible answers over here. The more interesting ones are when the tool actually say no. This tells you that there exists at least one state in your reachability graph that does not satisfy the invariance. You know what, since I kind of mentioned universal and also existential, why don't I open a new page and talk about it right away, right? A little bit ahead of my schedule today, but let's now just talk about it very quickly, okay? So one way to really understand the model checking problem is like this. So think about, so we're trying to formulate the model checking problem itself. Model checking problem. Okay. Okay, let me just write down the universal and existential quantification right away, but we'll see the syntax in more detail when we get there in the review. All right, let's just formulate that. So basically, with let's say given model or module, let's say. So this will be the word you're more used to from lab number 1. Given module, let's say n, and some invariant property. Let's say P. Right? So what's really the model checking problem? It's more like a universal quantification. We say for every states. All right? And then if S is a member of the reachability graph that's built from the model. The reachability graph of your model. That implies that P must be satisfied on the state S. As easy as that. All right, let me explain again. All right, so you can think about this guy here. RG is the reachability graph. And RG of n is more like all the reachable states from your model. All reachable states of the system being modeled. Okay, being modeled. And we're talking about all the reachable states. What if the state is not reachable? We don't care, right? You don't even need to worry about unreachable states. We simply don't, right? And that's also to do with the nature of the implication, which we'll also have to review today. All right, I'll get there. And let me just put some parentheses here, okay? That means we do not care. We don't care about unreachable states. If the state is not even reachable from your initial configuration, then of course no concern. It can do no harm to our safety property. All right, that's good. And that's number 1. And number 2, what does it really mean when we say we have found a counterexample? All right. So you can think about the number 1 here is more like the case of, sorry, just let me go back and forth a little bit. The universal quantification I just said is more like a yes, right? Because all the reachable states will satisfy the property. And what about the no here? Okay, let's now formulate this no here. Okay, the no here will be, this will be when there is a counterexample. Counter states. Okay, the way to formulate it would be, we'll say there exists S. First of all, S must be reachable. S must be reachable. It's in the nodes of the reachability graph. And not only that it's reachable, but also that state there doesn't satisfy the invariant. That's why I call it a counterexample. And not the case P of S. And what's more, good point. I'll just let you help yourself every time. Okay. All right, what's more, so this is like a witness for the invariant property. Guys, by the way, is here kind of visible to you guys? Kind of, right? Okay, in case you cannot see it, just let me know, all right? Yeah, but it's recorded anyway. All right, so this one here, you can think about it is the witness of invariant violation. And the model checking tool is going to give you a trace going from the initial states all the way to S. And a counter trace is going to look like this. The counter trace is going to be, if you remember the way we draw it, so we start with the initial states, and then we may have several, so I do kind of like a curved arrow to say there might be multiple states in between. And then we're going to reach this particular state called S, right? So that's the one that does not satisfy, right? So this is a very valuable information here called a counter trace. So the trace is going to say, start from here, the initial states, it can lead us to the first state that violates the invariant condition. So that's the trace. It's a very good debugging information for us. Guys, are we okay? I think that's a nice example for universal existential anyway. So I think just another example. Okay, just came to my mind. All right, very good. Okay, so let's go back to finish the recap, right? So that's good. So that I'll make sure I include it in today's notes. Okay, and then we have formulated the yes case, we have formulated the no case. And for this one here, we don't need to formulate. That simply means somehow you want to maybe prove about the universal quantification, but the computer simply has no power to go through all the infinite number of combinations for the input, right? State explosion. So we don't, it's not possible to formulate state explosion. Just too many things for us to consider. All right. All right, so that's about the 3 possible outcomes about the model checker. So just don't forget, this is also a legitimate outcome. Very possible, state explosion. All right. And then TRA plus, okay, so that's something you guys learned about from lab number 1. Either this Wednesday, Wednesday maybe not yet because your lab is only due on Thursday. Maybe next Monday where I can do some very quick recap about your lab number 1 and then give you some short introduction about lab number 2. Okay, I'll make sure I release lab number 2 by next Monday so you can also get started. Okay. All right, and then the comparison between the two courses, right? So we are focusing on modules over here. Okay, and just in case you guys have some doubts for your lab number 1, when you actually want to encode, for example, M1, which in the context of 3342, that one there you have in M0 just N, but you got M1 another set of variables A, B, and C. But now in TRA plus we don't have refinements. So what you got to do is you got to make sure all the 4 variables exist in the same module. And also whenever you want to do some updates to the variables, make sure you update all the variables in a way that's consistent. So you can be subject to some checks. Right? So that's something you got to watch out for lab number 1. Okay, I'll leave the details to you. All right, and then that's kind of the only thing we did in the review, which is about the AND and also OR operator, right? We just say that you want to be aware that in math, we got commutativity. But in programming, we don't really have that because of short circuit evaluation, right? So you guys can review the facts over here, all right? Pretty handy. All right, so that's kind of the exercise I gave to you guys. All right, so let's now discuss them very quickly, and then we can move on. Okay. So let's see over here. All right. So we got 2 possibility over here. Our goal really is to check whether or not array A at index I larger than or equal to 10. That's what we really want to check. But somehow we have to do some checks to make sure the index over here is valid. I kind of give you different orders about the conditions to check, right, over here. So we got option number 1, option number 2, right? I'll just give you the answer right away, but you guys got to think about it. In the test, I might give you maybe different, different order or different context. So in this case, it turns out neither this nor this will work all the time. That means there will be certain scenarios of I that can trigger some array index out of bound exception, right, for 1 and 2. Right? So now let's be a little bit more logical and see what's going to happen. All right? So let me just wipe it out. I hope you guys know what the question is, but you can also refer back to the notes from last time. All right? So answer number 1. Neither 1 nor 2 work all the time. Okay? Answer number 1. Neither 1 nor 2 works all the time. And of course, answer number 2 will be the part 2. You want to somehow figure out the precise scenario where it doesn't work for 1, and also the precise scenario that doesn't work for 2. Somehow these two scenarios are different, somehow. Okay? And the idea will be very simple. Okay? I'm not going to even bother you. You can see here for 1, we are only checking this one here to make sure I is not too large. I should be less than or equal to a.length minus 1, basically. All right? So now, for example, if I happen to be, let's say this. Let's say a.length is just 10. If I put I as too large, like 11, in that way, 11 is going to fail because 11 less than 10 is going to fail this. So it's going to give this one false here. That means it can protect this one here. We don't really continue, right? Agree? Okay. So if it happens to be 11, for example, in that way, short circuit evaluation will not evaluate AI. So we wouldn't run into the array index out of bound exception. On the other hand, you can see because evaluations will go from left to right. This condition here, making sure I is not too small, it must be at least 0. That one there is only checked after you have checked AI. That might be too late, right? Because this one should be evaluated first before this one here. So what you can think about is this one here. So let's give one example. Let's say, what if I is minus 1? It should not be even used in the first place for AI. But in that way, if I try, I will be minus 1. So you're going to evaluate from left to right. So minus 1 less than 10 will be true. That means we'll still actually get to here and use a minus 1. That's not good. So you're going to run into array index out of bound exception. Okay? So for 1, I larger than or equal to 0, check too late. And for example, I equals minus 1 will trigger array index out of bound exception. Array index out of bounds exception. All right. And for the second one, it's going to be very symmetric. Apparently for this one here, if you try minus 1, right? What used to fail for number 1 here. If I try minus 1 here, you can see minus 1 larger than or equal to 0 is false. So I wouldn't even get a chance to it. So it's properly guarded. That's good. However, what if I try, for example, 11 here that used to work for 1. But if I try 11, for example, if I try 11 here, it's only check over here. That's too late. So now 11 larger than or equal to 0 is going to be true. So I will still evaluate it like A11. Right? So that's the precise scenario where it wouldn't work. So what works for 1 would not work for 2 and vice versa. That's a conclusion. All right, so you guys can think about it, right? So I kind of mentioned all the details to you, but you really want to think about, if, for example, if I still got array indexing over here, but somehow I give you more conditions to consider or different organization, right? So you got to really judge by the same principle. So for 2, I less than a dot length, check to late. Too late. And for example, when I is equal to 11, they will trigger. Array index out of bound exception. All right, any question? Yes?
Professor, for the second one,
yeah.
Let's say the first condition, I greater than equal to 0, that's true.
Mm-hmm.
The second is also true when we have 11.
Mm-hmm.
And the third is false. It's gonna be checked late, but it's still gonna be false.
You will, no, I see what you mean.
Yeah.
I know exactly what you mean. So let's say I is 11. So we know that 11 larger than equal to 0 is true. So we got to evaluate this, okay? When we want to evaluate this over here, A11 is not going to give you anything. It's going to give you array index out of bound exception already. So you don't even get a chance to move on, right? So there's nothing else. So overall, it's not going to return false because if this one here, 11 larger than or equal to 0 is true, whether or not the whole thing is going to be true or false, we still got to see the evaluation for this one. Or potentially we got to see this one as well. But when we try to evaluate this one with 11, we're going to run into array index out of bound exception. So you don't really get false overall. Okay, yeah, think about it. Yeah. All right, guys, any other questions? All right, good. Right, that's good. All right, so now let's move on to, so that's really what I want to say about the conjunction and disjunction. You really want to kind of know the comparison between programming and also math. Okay, and let's now move on to the next operator, which is more fun, implication. Okay, implication usually is what's going to give us trouble. It's maybe not as intuitive or not as straightforward. So you will see that on the table here, I do have the table for you about implication. I think many of you already know pretty well about the true and false, right? Either by memorizing or you really know the true rationale behind. But let's just go over that, just for the sake of review. Let's now do that properly, just once, okay? All right, so the way to think about implication, P implies, the way we're going to write it is like a double line arrow. So maybe in your 1090, it's like a single line arrow. But for us, for this course, we're going to stick to double line arrow, okay, for that. So when you actually write for this course, we don't really write P implies Q. No, we don't do that, right? We're going to write P, we're going to do just double arrow. So P implies Q, all right? And let's now just talk about some very quick terminology, right? Just when we're going to use the implication quite a bit when we talk about temporal logic and also program verification, especially when you want to figure out sometimes it might just be evaluated true trivially, or it might be evaluated false, right? You're going to be very clear about different circumstances. So let's do that properly, okay? So in terms of terminology, you will also see on the slides, but I'll just put it here. So for the P here, to the left of the antecedent, to the left of the symbol, is called antecedents, or it's called assumption or premise. Doesn't matter which one you use, right? So these are the common names: antecedents, assumption, or premise. And as for the right-hand side to the symbol, it's usually called either the consequence or conclusion. Right, either way. All right, and then we're going to see how we can understand about the different rows in the truth table for the implication. So there is some analogy that's very useful that I'll just introduce to you, just in case you haven't heard about the story. All right, so we're going to talk about P implies Q over here is more about forming a contracts. Okay, I'll talk about it. And we say that the implication over here is going to evaluate to true if the contract somehow being formed is honored, meaning that it's not violated, it's not breached. Okay, so that's the idea. Right, I'll just switch to iPad here and let's talk about the story. So you can think about for antecedents over here, in terms of in the contract term, it's more like a promise term. When you sign a contract for your employment, there will be some promise terms to you. Maybe how much you get paid annually, also what kind of benefits you will get, right? Like medical insurance or whatever insurance, right? Promise term. For example, it could be your salary or it could be your benefits, employee benefits. On the other hand, you can think about the consequence over here is more like the obligation. Given that the promised terms by your employer are met, what's your obligation, right? Okay, so basically about what kind of work or duties you're supposed to fulfill. All right, so having this analogy here, we're going to talk about, okay, P implies Q over here. Overall, this implication would be true if the contract is honored. Or it might be convenient for you to also think about when I say the contract is honored, it simply means it's not breached, it's not violated. All right, let's now talk about 4 different cases because we got P and Q and their proposition true and false. So we got 4 different combinations. Okay, let's talk about the only case where the contract is honored. The only case. So case number 1. So if I got P over here, it's just true, and also Q is also true. That means the promise terms are really paid to you in time. And you also do the work. That's the only, well, that's, I should say, that's one of the non-trivial cases where the contract is honored. Sorry, when I said it's the only case, I was wrong. Okay, it's one of the, it's definitely the more non-trivial case where it is wrong, where it's honored. All right, so here, the P implies Q. Okay, P implies Q, just remember we put this in the row here. This will be true. Okay, so let's say this is the only case where it's true non-trivially. Only case where the implication is true non-trivially. Non-trivially in the case that you require both the promise term and also the obligation both to be true. All right. Okay, case number 2 here. Case number 2 is the only way to really make implication false. Meaning that if somehow P is true, that means your employer actually pay you and also gave you the benefits as promised, but somehow you didn't do the work, right? So that way, that'll be the only case where the contract is breached. Okay, so this is the only case where it's false. In this case, P implies Q will be false. Okay, this is the only case where the implication is false. The only way to make the contract breached. All right, the other 2 cases are to say, if somehow the promise terms are not really met. In that way, for you as an employee, whether you fulfill the obligation or not, doesn't matter. The contract is not breached. Okay. Okay, so we got C3 over here. Okay, so here, if we got P would be false, and also P would be false. Okay, in that way, it doesn't matter what Q is. Q could be true, and Q can be false. Doesn't really matter. But the result will be just true. All right. So you can see there are three cases where it can be true, but there's only one case is false. All right. Especially when the antecedent is false. In that way, it doesn't really matter what the consequence is. Okay. Okay. All right, that's good. Just about analogy, right? Maybe you know that already, but it's worth just covering that. Just make sure everybody can understand. All right, so after this, we're going to talk about there are different ways. There are also different ways for you to talk about implication. For example, when you, in your other courses, we talk about P if and only if Q, right? So if and also only if is sufficient, is necessary, unless, things like that. So you also got to understand those terminology. They are really talking about the same mathematical symbol here, like a double line arrow over here, but let's now talk about some intuition behind. So it'll be a little bit easier for you to kind of remember the saying. Okay, so this is what we just went over. Okay, the truth table. Okay, and about implication. So there are alternative way to really talk about the implication. Rather than saying P implies Q, we got different ways to say that in English. Okay, so let's now go over all of them. Okay. So I'm summarizing this page over here, and the way you want to go with this page over here. Memorizing it is really the last thing you want to do, because that wouldn't last for long. Maybe only within this course. Beyond this course, you still want to keep this knowledge. Okay. So the way I will try to help you understand is the way they kind of describe this in English is really to do with the truth table. Right? That's really the truth table you want to take a look. All right. Okay, let's take a look at this one here. When I say Q if P, that is to say, given that, so Q will be true if P is true. So P will be actually the condition in order to make Q true. So that's really what Q if P really mean. Right? Q if P. Okay. So if you look at the truth table over here, you can look at this one here, Q if P. They're really talking about these two rows. Q if P. This row here. So if you think about this row here, just this row. If you can look at this row here, Q is true if P is also true. And they are both true. So that's why the implication here is actually true. Given that P is true, Q is also true. This will satisfy exactly what's really said over here in English. But what about the other remaining three rows? Is somehow also covered implicitly. This row here is saying, well, P is already true, but Q is not. P itself should really ensure Q is actually true, but it's not true. So that's why overall the implication should be false. Okay, I'll write it down. So this one here, P is true, but Q does not follow that. So the implication is false. All right, and the remaining two cases over here, you can see we simply got false. When we talk about Q if P, so we are saying if P is actually true, but what if P is not true? Then we don't care. In that case, Q can be either true or false, doesn't matter. So the implication there will still be true. Okay? So you can simply say here, false over here, if P, right? So here you can think about when P is not true, we don't care what Q is. All right. So what you really want to focus on will be, so based on this English description here, how does it really correspond to all the 4 rows, either explicitly or implicitly? Right? So that will be how I would advise you will understand this kind of informal saying. Right, there's another saying which is pretty much the same process. I'll just go over that just one more, just like a recap. Okay? P will be sufficient for Q. That means if P is already true, that will be sufficient enough to conclude that Q is also true. Right? That's sufficient for, really means. So the only way to really make it true is this row, just the same. I know that P is already true. That should be sufficient for Q to be true. And in this case, Q indeed is true. So overall, it should be true. Right? That's the only case. On the other hand, P here is already true, which should be sufficient for Q to be true. But Q in this case is actually false. That's not good. So that's why the whole implication is going to be false. Okay? What about when P here is simply just false? But when we describe this, we say that P being true is sufficient for, but if P is already false, then we don't know. It cannot be sufficient for anything. So that's why it doesn't matter what Q is, the implication is not violated. We simply don't know those cases. Okay? Guys, are we okay about this? Okay, think about it. If there's a particular one you want me to repeat next time, do let me know, or just drop by my office hour so I can know where you might just get confused. Okay, think about it. Okay, let's talk about this one here. Okay, very quickly. This one here is kind of go the opposite way. So now we talk about only if. Okay, so here when you say P only if Q, right? What does that really mean? That means if I know that P is already true, then the only way to make this implication true is for Q to be true as well. That's what only if really means. Okay? So now, how does this work? So think about, again, it's really this line here. The same process. So this one here, we know, knowing that P is true, the only way to make the implication, to make P implies Q true, is when Q is true as well. Right? So here we are basically talking about P here, and P implies Q, and also Q, right? Knowing that P is already true, the only way to make P implies Q true is for Q to be true as well. That's exactly this row over here. What about other rows? Very similar arguments. So if P is already true, the only way to make this one true is for this one to be true. But this one happened to be false, so it has to be false. All right. And so here we talk about P is already true, but if P is already false, we don't care. Right? Implication here is just not violated, so it will be true. All right. And you can argue the same way for necessary. So let's just talk about this row here. If I know that P is already true, then it would be necessary for Q to be true as well in order for P implies Q to be true. And in this row, indeed, it is the case, because I know that Q is already true. So that this condition here is satisfied. On the other hand, for this one here, P is already true. It's necessary for Q to be true in order for this one to be true. But Q is false. So implication cannot be true. So it got to be false. All right. And so here, so when we say P is actually already false, right? Then we don't care. about this one here. Doesn't really matter. Okay. Yeah, so these two are kind of similar, but you just got to watch out the order of the where you put the propositions. Okay. Okay, final one. All right. Final one is about Q unless not P. Okay. Think about here. This one is also this one deserves a little bit more visual illustration here. So here we say, in order for implication to be true, is either Q is true, but if Q is not true, then what about not P? If not P is also the case, then the implication will also be true. Okay, I'll show it to you. So this one here really enumerates the two scenario for P implies Q to be true. Either it could be Q, right? Let's see why. You can see if Q is true, and Q is true over here. In both cases, the corresponding row for implication is just true. Right? So we covered two rows already. We're basically enumerating about under what circumstances can we actually make P implies Q true. So two possible. So the Q here tells you if Q is already true, then P implies Q must be true at the same time, right? According to the truth table. What about the next condition? What if Q is not true? Unless not P. So that means not P is actually true. Not P is true means P is false, right? That means P is false. And if you look at the row, so P is false. These two rows. And they simply correspond to, over here, the true here and also the true here, right? They kind of overlap, which is okay. Okay, recap, and then I'll need to talk about the remaining row as well. So Q unless not P. Basically enumerate about all the three possible rows where you can make P implies Q simply true. So when I say Q, that means either this or this, both true. Then the corresponding P implies Q, also true, right? That's the first condition. And the second condition tells you if the P here is already false, which will be these two rows. And indeed, they also correspond to true. Now we're missing one row, right? The row we are missing is over here. And indeed, that's the only case where P implies Q will be false. And this one here, if you think about it, if neither this nor this is the case, that will be the only row where implication will be false. So this will be when we got not Q and P. So this is the only case to make the implication false. So here we don't have Q anymore, we just got not Q. And also we don't have not P, we got just P. Exactly the negation of the two conditions here. If both of these conditions are simply violated, which will be this row here, that will make implication false. All right. Could be a little bit tricky for the first time if you haven't been really used to, for example, this kind of notion here, or maybe only if, right? Just get used to it, right? So these are important stuff when we talk about proposition. All right, any question? All right. There is one theorem which you guys don't need to prove. You can take it for granted. We can also rewrite the implication by using some other logical operator, right? I'm pretty sure you have seen that. I'll just mention that. That might be something you will need to use later, okay? So P implies Q is equivalent to not P or Q, right? I'm pretty sure I've seen that before. All right, good. Okay, you might be wondering, so what can I ask you in the test about this? Oh, quite many things, right? I'll give you one example, okay? That might give you some guidance about how to get prepared. But as I said, guys, it would be your least interest just to memorize about things. It might be better, before you ever try to memorize, to really understand how this informal description here really corresponds to the different parts of the truth table. That'll be really the best way to understand the operators. That's how I did it. Okay. All right, so I'll give you some example here, and then we'll take a short break pretty soon. Okay. So one example question could be, of course, it's maybe on the easy side, but you guys just get some idea. So which of the following expressions are equivalent to P implies Q? Okay, it's a simple one, so I'll just give you two choices, right? So I'll put a box over here, right? Now radio button, so it could be multiple choice, multiple correct answer. I can say Q if P, Q, okay, if, only if. Pretty easy, huh? But, you know, you get the idea, right? All right, in this case, which choices should I pick? So let's say this might be choice number 1, choice number 2. Should I pick both 1 and 2? Not really, right? All right, it turns out, okay, I'll just answer for you. This one here. All right? Q if P, because we said earlier, Q will be true if P is already true, right? That's kind of how we explain. And this one is not good because you guys, once you guys study, you will see more. For now, you might still be a little bit lost, you know, in all the terminology that we talk about. So this one here simply corresponds to Q implies P, right? Where we say Q only if P. So given that Q is already true, the only way to make the implication true is when P is true. So that's exactly this implication, not the one being asked. All right, so this one should not be chosen. All right. If you chose that in E-class, of course, you will get some deduction, right? That's the E-class scheme. I'll give you guys more examples on other aspects. But for this one here, you see the idea, right? So you really want to get yourself familiar with all the different sayings. So this is one thing here, and then I want to talk about just one more thing, and then we'll take a short break. What about if and only if? That's also very important. Okay. Just show you how to understand it. Okay. Whenever we say we want to prove so let's say we got some predicate, some assertion, right? P just some Boolean expression. P and Q, we want to show that they are equivalent with an if and only if. All right. So the way I understand that is like a P if and only if. Okay. So think about this part over here is the if part. And this part over here is the only if part. Okay, so let's now write it down quickly. Yeah, so the way I write it usually, I would say P if and only if Q. All right, good. Maybe that's what you're doing already, which is good. Oh, what do we need to prove? So in order to prove that, we need to prove two things separately. It's like in order to prove a single sequence, you can prove two sequences independently. Similar idea. Need to prove two things. Number one, you will prove that P if Q. And also number two, you'll put P only if Q. All right, for this one here, the second one is pretty straightforward, right? P only if Q. That's exactly how we explain about only if. So this one here is really P only if Q. But here, this one here, you can think about the implication. Yeah, this one here, don't really use that, right, in the actual paper, right? You know, when you write things. This one would be equivalent to Q implies P, right? right? When you say Q implies P, that's exactly P if Q, right? P will be true, given that Q is true. So this one will be P if Q. Yeah, if and only if. That's also mentioned in the slides, but I thought just building that from scratch can help. Okay. All right, guys, any question? Okay, about implication, right? Basic, but I think it's good to know. Also important to brush up. Okay, why don't we take a very short break by taking attendance? Okay. All right, so before the break, we finished discussing implication. There's some other property I also need to talk about. Just bear with me. The pace could be a little bit slow about the math review, but we really need them later for temporal logic and also program verification, right? It's going to be worth our time. All right, so these are what we talked about before the break, right? You guys can go over again, and the key will be to really use these English description, connect them to the truth table. That will be the best way to really get a more program in your mind. All right, so these are the ones, and then, okay, so just very quickly about like inverse, converse, and contrapositive, right? I might just give you one of the questions I gave to my 43, either 3342, 4315, like a written test question, right? So let me just show to you very quickly, right? So you can kind of see what can be expected if I need to put this one in the test, okay? So why don't we say over here, so let's say this will be some example. So let's go with the order that's in the slides. Let me just remind myself very quickly. So we got inverse, converse, and contrapositive, right? So we got inverse, converse, and also contrapositive. All right, good. And let's use some kind of like a concrete example here, just using x and y. So the example we're going to use is, let's say, x larger than 0 and x less than or equal to 23 implies y larger than or equal to 23 or y less than 46, right? Just two variables. That's an integer. And that's the implication. Right? So the ultimate question I might just ask you would be, what's the contrapositive of this particular implication? I might just ask you about contrapositive right away, but in order to construct that, you will need both the inverse and converse. So we can talk about all these, right? Just as a complete example. All right? Let's have our inverse first. So first of all, inverse. Okay, for inverse, according to the definition, if you got P implies Q, inverse will just be not P implies not Q, just apply negation. All right, so we can also try to simplify using some nice little property called De Morgan. Okay, so think about this is like a P and this is like a Q, right? So we're going to turn that into not P implies not Q. Okay, that's what we'll do. So it's going to be not x larger than 0 and x less than implies not y larger than or equal to 23 or y less than 46. Okay, let's now do a little bit simplification here. And for De Morgan, let's remind ourselves very quickly, we need De Morgan also quite often. Okay, I'm pretty sure you also know, if I say not P and Q, should be not P or not Q. If I get not P or Q, should be not P and not Q. Right? You can take that for granted for this course. All right. So for this one here, let's see, which is equivalent to. So this is something called the equivalent equational proof style of presentation. That's something we're going to stick to not for the model checking part, but more to the program verification part. So I'll show to you, I got this example here about when we do some little proof about quantification, maybe not today, maybe on Wednesday. So I will also show you again, right? That'll be the style you have to stick to, especially for the final exam. Okay. So this one will be equivalent to, all right, so here, De Morgan. So think about equivalent, you know what it really means. And this one here, you can think about this is more like a justification, right? So this part here is the justification for one step. If I want to go from one thing into another thing, I need some justification. Pretty much like a sequence, really, right? If you want to go from one sequence to another, you need some inference rule. Similar idea, right? And this is something called equational proof style. Equational style of proofs. Right? This will be very handy. I even remember maybe in some temporal logic, like a property proof, we also use equational. We don't really use sequence in this course, right? Mainly equational. Okay, it's quite nice. All right, so for this one here, so after this, we can simply say, if I say not x larger than 0, you will agree it should be x less than or equal to 0, right? That one there, I'm pretty sure you know. So x less than or equal to 0, and change from n to or, and also, okay, so not this or not this, right? So this will be turned into larger than, okay? X larger than 23. That one implies, and similarly, so this will be another De Morgan. The one we just used a De Morgan for n. So now it will be De Morgan for or, okay? So not this, and then turn this to n, not this, okay? So it'll be y less than 23 and y larger than or equal to 46. So once we got the simplification here, we can just use it, right, for later. We don't need to do the same simplification just to repeat. We don't need to. All right, that's about inverse. And we got the second one called converse. Converse, according to the definition, will just be no negation involved, so there's no De Morgan. We'll just say swap the order of the antecedents and the consequence, right? Let's just do that. So converse over here, this is what we're given. This is a P, that's a Q, right? P and Q. Rather than P implies Q, we're going to say Q implies P. Okay, that's a converse. Just y larger than or equal to 23 or y less than 46 implies x larger than 0 and x less than or equal to 23. All right, so far so good. And the final one, contrapositive. By definition, is simply the converse of the inverse, basically, right? You can think about you get not P implies not Q first, and then you kind of swap the order. So that becomes not Q implies not P, right? So converse of the inverse. Okay, I'll put it here. So the one we want to do will be contrapositive. Let me just move that a little bit up. Contrapositive is the converse of the inverse. Well, you want to say inverse or converse, that will also work. Okay. Okay, converse of inverse. And we got inverse already, right? So we can reuse it. So that's the inverse. How do we take its converse? Switch this one to be antecedent and switch this one to be conclusion, right? Just switch that. So I can just do that directly. So think about this guy here. Y less than 23 and y larger than or equal to 46 implies Okay, so this guy here, x less than equal to 0 or x larger than 23. All right, contrapositive. And interestingly, there is another theorem that's also called contrapositive. Right? I'll just mention that here. It's also relevant. When I say P implies Q, it is equivalent to not Q implies not P. All right, I'm pretty sure I've seen that, right? So you can think about this is the contrapositive that we just spoke about. So you can go from one implication to its contrapositive. And the theorem of contrapositive tells you that these two are equivalent. Right? It's kind of relevant. Okay, I think this one here, we might have to use it quite often too. Okay, yeah, if there's anything I can come up with right away, I will just mention them, right? You don't really need any extra theorems for proving purpose for this course. If there's any particular one you need, I'll always let you know. All right, just make your life a little bit easier. All right, that's good. And then a little bit more properties, right? We've got about 15 minutes. Just go a little bit more, right? So we might be able to reach a little bit to quantification. Okay, propositional logic. Okay, so we just got, yeah, P implies Q will be not P or Q. Already mentioned to you. Okay, we got something called identity, right? I will just use another page to discuss this quickly. We basically got identities and zeros for propositions. Let's do that quickly. All right, so we got, let me start with identities. Identity simply means if you apply that particular value with the operator, it's going to give you something itself back. For example, if I say the plus operator, and also I got a multiplication operator, right? I'm pretty sure you guys know pretty well. In order to get the identity, I should really get just the A back, right? For plus, it will be 0. For multiplication, it will be 1. Right? That's identity. I'm pretty sure you know. And for logic, just the same thing. So let's now talk about the identities for 3 different logical operators. So we got, let's say, implication. Something implies P. And if the something here is the identity, I want to get the same P back. And also, if I say, let's say, and P, I want to also get P back. Or here, I also want to get P back, right? That's exactly what identity really means. If you apply that value there, and with a logical operator, with some proposition, you get the same proposition back. All right, guys, your turn. What should this be? False, are you sure? Remember, false implies anything will just be true. That's not identity, all right? Watch out, okay? If that's not false, it gotta be true, right? Okay, good. All right, gotta watch out. Okay, I will excuse you guys today because you just gotta review, right? You really gotta study that. Just for this one here, right? If you go back to the table here, right? You can see that if you look at the table here, right? Just want to show you right away why it's called identity. Let's say here, true will be the identity for implication because now if the second one here is true, it will just be true. If the second one is false, it will be false. So it really corresponds to what Q is. That's why it's called identity. All right, good. The same can be argued also for conjunction and disjunction. All right, guys, what should be the identity for conjunction? True, true. Okay, good. Thank you. And that one there, not gonna bother you, it'll be false. All right, that's identity, right? You can see how that can be derived, right? Don't need to memorize. Oh, okay. And what you guys maybe really meant to say was the zeros. 0 simply means, let's say, imply here. Oh, and then I will do and here. And also or here. If I apply the 0 of the operator over here and given some proposition, I will simply get some constant back. Doesn't need to be true or false as long as it's a constant that's always given back. That means I got more like a 0 flexibility over there about what the answer should be, right? So here you do have some flexibility, right? Okay, so here equivalent to, equivalent to, equivalent to. So now you may want to figure out two things over here. Basically, the 0 should be some value over here such that if I apply this value here is always fixed. It will not depend on this second operand here. I'll write it down and then you guys tell me. Just give me one moment. When the zero of implication is the antecedents, the value of the consequence is always fixed. Is fixed. All right, guys, just for this one here. What should I put here and here? You may want to think about different combination, right? For example, if I say true over here, is this one already fixed? Not really, kind of depends, right? If this is already true, then it depends on what P is, right? That's really what the identity is, right? So it turns out if I put false over here, right? So false implies anything. So that means this will always be true. Does not depend on what P is, all right? All right, similarly, if I put false over here, this will always be false. And if I put true over here, this will always be true. Doesn't really matter what P is. And the 0 here is really the basis for short circuit evaluation, right? You can also notice that. This is really the logical basis of short circuit evaluation. All right, good. I think somehow on my notes, I also have some notes for you about the precedence, about the order of applying the logical operator. I'll put it here too, okay? Precedence. Okay, so negation will always be the highest one, and followed by conjunction, followed by disjunction, followed by implication, and then equivalence. So, for example, if I say not P and Q or R, for example, right? Well, so this one here, this would go the tightest. All right, so this one should be evaluated first. And then comparing this and should really be evaluated first. So that means this one should be also evaluated first before you can do the disjunction. This will give you a little bit of flavor about when we get to temporal logic, we're going to introduce different operators. And once we know about their precedence, we're going to do some fun exercise about building some syntax tree. I know you guys haven't taken 2001, the theory of computation, but we'll do a little bit syntax tree. It's quite intuitive, right? That's something we have to understand before we can understand the temporal formula. All right. I got 6 minutes. Let me do a little bit, okay? All right, let's now talk about maybe a little bit predicate. No more, no less. 6 minutes. All right, I think everything has been mentioned already, right? So these are all handy stuff for logic. Okay, predicate logic, right? So let's see how far we can go. So a predicate, as opposed to proposition, is more like you have range. So whenever you see universe of disclosure here, that means we may have arbitrary range for variables as opposed to just true and false. In some way, true and false is also like a range of size 2. But now, if you talk about universe of disclosure, it's a much more general term about range. Right? So it can be an interval, it can be a natural number, but I think in your TL, in your Pascal, it's more often to get intervals, as you will see. Okay. Okay, and then variables on range, right? So that's really the extension we are making about the to the propositional logic. All right, so let's now talk about, these two are pretty straightforward, but just good to emphasize. So we got two number sets over here, right? Because I know for some of you, you might be thinking natural number in a different way. So let's clarify this, right? Just make sure. So whenever you see this n here, which you also have seen in 3342, it will be the set of natural numbers. Natural numbers. And just remember, that one there includes 0. You'll be from 0, 1, to all the non-negative. Non-negative. Right, so just remember, 0 is included. All right? And then also we got the set of integers. That'll be z. Integers. And that one, they'll be straightforward. Basically, in theory, from minus infinity all the way to 0, all the way to plus infinity. Right? Just clarify right away, especially for natural number. Don't be confused, right? It does include 0 for our purpose. Okay, and then I'll get to the quantification, but let me just give you guys some very quick syntax lookup, very quick. Okay. So let's do some quick comparison. That'll be the last one for today, and then we'll review the syntax for universal and also existential more thoroughly on Wednesday. So let's now talk about syntax, which will be useful for your lab number 2. Okay. So if you recall how you write like an ASCII syntax for rodent for quantification, right? So in rodent, do you guys remember the symbol for universal? Anybody? If you remember. Some of you may have put it on your data sheets, I know. If you forgot, that's okay. Okay, exclamation mark, all right? So that one there, you say for every x and then colon, and then some range, implication, and also p. Okay, what about existential? It will be the hash sign, all right? There exists some x, and then and px. All right, that's for rodent. For every, that one is exist. Right, I'll speak more about exactly the meaning when we get there on Wednesday. Let me just give you some very quick reference for what's going to be important for your programming test, right? TLA plus or Pascal. This is something you will definitely get very familiar with anyway from lab number 2, 3, and 4. All right, so this is what you got to write. /A, like all right? And then you're going to say x, rather than colon, you're going to say in, /in. And then natural number, for example, you might say net. And also another one, comma, y, also in, maybe integer. And then this colon here is more like an implication, okay? Right, this is what you gotta write in general in TLA plus, all right? So think about this guy here is like a for all. And this guy here is more like colon, well, membership. And it's comma separated. Okay, let me mention about existential and then we're done. Okay, bear with me, 2 minutes. Okay. And very similar, you would say /E existential. X and then in natural number and also Y in natural number int and then colon here P of X. However, you got to be very careful. In the case of rodent, we got implication here and conjunction here. I'll speak more about these. We need that kind of foundation. But in TLA plus, it somehow overloaded the operator. So this one here really means implication. And this one here really means conjunction. All right, and finally, this part over here that's comma separated is about the range. Okay, I'll speak more about this on Wednesday. Thank you. Okay, just make sure you complete lab number 1 as soon as you can. All right, see you on Wednesday.